So this is chapter 2, Measurements and the Metric System. If you read chapter 2 in your book, then you read about the case study in which there was this informant who got whacked by the mafia. Anyway, the reason for that introduction was to introduce to you the very important skills of taking careful measurement. In fact, if I did a little research in terms of CSI investigation, and the Bertillon system is actually the system that law enforcement use in order to gather evidence and to make sure that the evidence holds water. The Bertillon system uh, was based on the invention of photograph, and police began to keep galleries of photos, disorganized photographic collection of suspects and convicts. That was needed back then because they needed a way to identify certain crime scenes. And in 1879, Alfonso Bertillon invented a method that combined detailed measurements and classification of unique features with frontal and profile photographs of suspects, uh, and which recorded the information on standardized card in an orderly fashion. The Bertillon system was based on five principal measurements: the head length, the head breadth, the length of the middle finger, the length of the left foot. I don't know why the left foot. The length of the cubit, that's the forearm to the elbow, to the extremity of the middle finger. Each principal heading was further subdivided into three classes of small, medium, and large. The length of the little finger, the eye color were also recorded. The Bertillon system was later overtaken by fingerprint, but the Bertillon mugshot has endured. And in this photo that you see here, it shows how these measurements were done. And Alfonso Bertillon said that every measurement slowly reveals the working of the criminal. Careful observations and patience will reveal the truth. He was ahead of his time in terms of forensic investigation, and this is the big principle by which scientists carry out measurements and conduct experiments. Now, whenever there's a crime, it's important to follow the chain of custody. You have to preserve the evidence. An understanding of the rules governing chain of custody is vital for an investigator. For example, in a sexual assault incident, the victim is typically transported to another location to have sexual assault examinations performed. Many jurisdictions have established a team to perform these examinations, and they go by several names such as Sexual Assault Victim Examination, SAVE. There's also Sexual Assault Nurse Examiner, SANE, Sexual Assault Response Team, SART, and many others. The examination involves the collection of victims' clothes, hair samples, swabs of bodily fluid, and documentations of bruises and bite marks. The materials collected are packaged by the team's member, and they make sure that these evidence go through a chain of custody so that it can stand within the court of law. Proper evidence packaging include appropriate packaging and labeling of all items, each item properly sealed and marked, correct and consistent information recorded in labels and procedural documents. You've probably heard that evidence is thrown out if it's contaminated. Well, that's why they take great pains to make sure that these evidence do not get cross-contaminated. So here's a little interactive demo. If you want to go to this website, you can be a forensic scientist for this particular interactive tutorial. In this particular tutorial, you have a body that was discovered, a fatal gunshot wound to the chest, probably indicating homicide. The forensic entomologist, that's your job is to figure out exactly the minimum elapsed time between death and discovery. So these are the tools, and if you go to this interaction, maybe you could determine how long, or what evidence indicates the time of death. So here's another photo. I think this came from your book, and you can see that it looks like a mess right now, but to a forensic scientist, this has a lot of evidence, and they would take a lot of measurements so that they can gather it for evidence. The blood splattering is also clues as to how these victims got killed, whether it be a stab wound or a gunshot. So this particular chapter is about measurements and making careful observations. So in making careful observations, you're making physical observations of the item. So let's review again the difference between a physical and a chemical change. A physical change is something in which the physical property is altered. When matter changes appearance, but the atom connection, the structure of the chemical stays intact, then that's what you call a physical change. A chemical change is when the chemical property changes because now it has a different type of chemical interaction. When matter changes its identity, bonds are broken, new bonds are formed, and the atoms are connected differently. This substance is therefore different. And so not only does a physical change occur, but the chemical properties are altered. Physical properties include refractive index, how it hits light and refracts the light, the density of the substance, the specific heat, the freezing point and boiling point of the material, the mass, the volume, the area, even the color, are some properties of that particular substance, physical properties. Now, we've seen this slide before in chapter 1, and it just gives you examples of physical versus chemical change. Sugar dissolving, cutting wood, applying glue, melting ice, breaking glass. Those are all examples of physical changes. Chemical change is when you change the identity, like heating sugar, burning wood, when you synthesize a material, when you break down a chemical, like the electrolysis of water, or when you force a chemical, an atom, to be embedded in another chemical, like doping glass. So we do take measurements in our daily lives. You might not know that, but in our daily lives we take measurements. Like you go to Starbucks and you ask for a venti or a grande. That's a measurement. That's the size of the coffee that you want. You go to the gas station and you fill up your tank. How many gallons did you take in your car? How much did you pay? These are all measurements. What time did you wake up this morning? How fast did you drive to school? Nurses, doctors, detectives, scientists, they all have a profession that requires careful measurements, and they have to be skilled in making sure that their measurements are consistent. In fact, if you take measurements, then you're talking the language of science, math. Scientists make countless measurements during their experiment to prove or disprove a theory, and math is the language they use to do that. So, when you take a measurement, like for example, what is the response that you would think of if I say I weigh 64.4? Well, your immediate response would be that your instructor is like the size of a child. 64 pounds is very light, probably half your mass, or for some of you probably a quarter or half, a third of your mass. But if I told you that that is 64.4 kilograms, then it defines the type of measurement you're doing and the magnitude of that particular measurement. So whenever you take a measurement, you got to make sure that you have the magnitude, the number, as well as the units. The units is just as important. A measurement without units is really meaningless unless it's been defined. So one of the most common unit that you will measure is the mass, but mass is not quite the same as weight. Yeah, here in this country we use it interchangeably, but if you're a scientist, especially if you studied physics, you know that weight is based on the gravitational pull of planet Earth or the moon or Mars, whereas mass is the amount of matter that that particular substance contains. So let me just show you a little snippet of the difference between mass and weight.
Eureka! The story so far. All masses attract all other masses to a certain extent. The Earth, being a very large mass, exerts a very large force of attraction which is called the force of gravity. This pulls all objects towards the Earth at an acceleration of roughly 10 meters per second per second. The force of gravity acting on a mass of 100 grams is called 1 Newton. And now, weight versus mass. If anybody ever asks you what a Newton is, yes, you could give them an apple, or a couple of golf balls for that matter, or a small flashlight battery, because all of these have a mass of about 100 grams. And when the Earth pulls them down with an acceleration of 10 meters per second, we say that the force of gravity acting on them is 1 Newton, or that the apple, the 2 golf balls, and the flashlight battery are all pulled down to Earth by a force of 1 Newton. How many newtons are pulling you down to Earth? Well, the simplest way to measure a force is to use a Newton spring scale. If we hang the apple on it, we see that the Earth is pulling the apple down with a force of 1 Newton. And if we hang you on the spring scale, we see that the Earth is pulling you down with a force of, let's see, just about 600 newtons. So now we know how much you weigh. What you weigh merely means what force of gravity is pulling you down to Earth. That's all weight is, the force of gravity. Remember how keen physicists are on Latin words? Well, gravity comes from gravitas, which is simply Latin for weight. But you thought you were weighed in kilograms, didn't you? That's true in everyday life, but not in physics, which has to be very careful about these things. In physics, kilograms measure your mass on a balance, but your weight is always measured in newtons on a spring scale. You'll have noticed by now that you can usually work out the number of newtons by multiplying the kilograms by 10. 100 grams, or 1/10 of a kilogram, is about the same as 1 Newton, and 60 kilograms are about the same as 600 newtons. But if 1 kilogram is the equivalent of 10 newtons, why bother to make a distinction between a mass of 60 kilograms and a weight of 600 newtons if they both really come to the same thing? To find the answer to that, let's go to the moon. It doesn't feel as if you weigh so much here, does it? Let's see how many newtons are pulling you down on the moon. Only 100. Why is that? Because the moon is much smaller than the Earth, and therefore has much less mass. So its force of gravity is also much smaller, only 1/6 that of the Earth, in fact. This is why your weight on the moon is only 1/6 of your weight on Earth. What about your mass? On Earth, it was 60 kilograms. How much will it be on the moon? 60 kilograms. Exactly the same, of course. You don't get any smaller by going to the moon. You don't change. Only the force of gravity, and therefore your weight changes. That's the big difference between mass and weight. Wherever you go in the universe, your mass stays the same. Only your weight changes. So if you're not as slim as you'd like to be, don't eat so much. You should join the Mass Watchers Club, because you've got a mass problem. But if all you want to do is lose weight, go to the moon.
see the difference between mass and weight. We usually use it interchangeably, but to a scientist, especially a physicist, they actually are different. So let's review the systems of measurement. In America, we use the English system. In fact, America and probably some country in Libya and Myanmar, Southeast Asia, are the only countries that still use the English system. Even the English don't even use the English system. They've converted a while back. In science, the rest of the world, I mean, uses the metric system. And the metric system is actually a convenient system of measurement because it's based on factors of 10. In the English system, you have to know that there are 5280 feet in 1 mile. You have to know that there are 12 inches in 1 foot. So these numbers are numbers that are not easily remembered. But in the metric system, everything's related by factors of 10. There's 100 centimeters in 1 meter. There's 1,000 meters in 1 kilometer. There's 1 million micrometers in 1 meter. So you don't have to remember different numbers, just the magnitudes or how large by factors of 10 these numbers are. For scientists, we use something called the SI, Le Système International, and it's basically a subset of the metric system, but it uses only 7 base units to measure everything in our universe. Let me talk to you more about Le Système International and what we mean by base units. So, units give meaning to measurements. Units such as feet, meters, inches, centimeters, measures length. When you have a unit of miles per hour or kilometers per minute, that measures the speed. You can see that some of these units are single units, or some of these units are combinations of units, and they give meaning in terms of what's being measured. So here is a graph illustrating to you which countries have adopted the metric system. In fact, the metric system was probably first started by France back in 1795, and most countries followed suit. Okay, this particular graph goes as far as 1998, so the most recent countries aren't really here, but you can see that America is nowhere in sight. So, in terms of the SI system, the metric system, again, is convenient because it's based on a factor of 10. The SI system is the set of units that scientists use, and there are 7 quantities in which all measurements are derived from. So let's take a look at these. For length, it's meters, not feet. It's meters with a capital M. Mass is kilograms, not grams. Kilograms, kg. Time is seconds, not years or hours or minutes. It's seconds. Temperature is measured in Kelvin, not Celsius or Fahrenheit. Fahrenheit is the US, Celsius is the metric, Kelvin is the SI. Amount, how much matter do you have? That's mole, M-O-L-E, abbreviated. Electrical currents called amperes, and luminescence intensity is candela. The last two, electrical current and luminescence intensity, are generally not used in chemistry. At least we won't be using it, but the first 5 are certainly used constantly. So if you take a look at this particular chart, what you see is that all these base units right here can give you other units. In fact, if you take a look at volume, volume is nothing more than meters times meters times meters. And so that's a meter cube right here. In fact, if you take centimeters times centimeters times centimeters, and you have 1,000 centimeter cube, that's 1,000 milliliter, and that's 1 liter. So here you can see from this particular chart that all of our derived units, these are derived units, are based on these 7 fundamental base units. So here are other examples of derived units. and it just gives you an idea that we do take a lot of measurements, and that we measure everything from the size of the sun to the height of Mount Everest to the diameter of a baseball or the loudness of a, say, fireworks show. That is all measurements, and we have 7 base units that can do that. So in terms of the SI, we do use the metric system in terms of the magnitude, and so it uses a series of prefixes to indicate the size. So a mega, like if you remember, if you have a hard drive, you got 600 megabytes worth of memory. Well, mega means 1 million. So you basically have, if you've got 600 megabytes of memory, you've got 600 million bytes of memory. So mega is 10 to the 6. A million is the factor. A kilo is 1,000. If you got a kilogram, it means 1,000 grams. Okay. A deci is a factor of 1/10. So decimeter is taking a meter stick, chopping it to equal size to 10 parts. One of those is a decimeter. So it's 1/10. That's the factor. A centi is taking a meter stick, chopping it in equal parts to 100 pieces. One of those is a centimeter. A milli is taking a meter stick, chopping the meter stick to equal size to 1,000 pieces. 1,000 pieces. One of those is a millimeter. A micro, which you can't even see, is taking that same meter stick, chopping it 1,000,000 times in equal parts. One of those is a micrometer. Nano, that's about the size of an atom now. You take a meter stick, you chop it off to 1,000,000,000 pieces. One of those is a nanometer. And pico, wow, that's really, really, really small. You take a meter stick, chop it to 1,000,000,000,000. 1,000,000,000,000 pieces of equal size. That's the size of a picometer. When you get to about a picometer, you're about getting to the size of the subatomic particles, the protons, the neutrons, the nucleus of an atom. So here is the chart again, and it shows you the fraction, the decimal, the exponent, and its conversion. So, like I said, the English system is difficult because you have to memorize the conversion. That, for example, 26 miles, 385 feet. If you have 1,000, on the other hand, the metric system is way easier to remember. Okay, so in this particular case, suppose you want to convert miles to inches. Well, you need to remember all these conversion factors. It's not easy to do. And here's an example of how many inches there are in 26 miles. You take 26 miles and you find the conversion between miles and inches. And I use this conversion right here. And what happens if you take 26 miles and multiply by this ratio, and this ratio is nothing more than 1, because 63,360 inches is 1 mile. The units of miles cancel out, and you get the conversion of how many inches are in 26 miles. In this particular case, it's 1,647,360 inches. But later on, we're going to learn about significant figures. There are 2 significant figures in your original measurement, so we take this number and we round it off to 1.6 million inches. So, let's go to dimensional analysis, because if you're going to learn anything in science, one of the things that you really want to know is dimensional analysis, because dimensional analysis actually allows you to solve many different types of problems. And it's very important if you're going to take chemistry later on. It's the way you solve a lot of problems in chemistry or physics or any of your science courses. So let me give you an idea of what dimensional analysis is about. Consider traveling abroad, and if you travel to, say, Italy, and the people there, I know that most Italians can't speak English, but suppose you go to a remote town and you land on the airport and you need to get to a hotel. How do you tell a taxi driver who cannot speak English that you want to go from the airport to the hotel that is off the beaten path? Well, the best way is actually use a translator, English Italian conversion translator book. Okay, and if you have that, then you can communicate the desire that you have, the given information, to your goal, getting to the hotel. Well, that's basically the essence of dimensional analysis. In dimensional analysis, you have a question, you're given some information, and you're asked to determine the solution. You're asked to determine the goal, and the goal is to